In this lecture, we continue our exploration of Laplace transform for integrals. Now, we have already seen one type of integral, which is the first one here. So, we have seen integrals, Laplace transform of integrals of the type 0 to t fu du. So, this we saw in the last lecture, but I will give another example where we can evaluate for a special function known as error function, the Laplace transform for this kind of integral. The second one is the Laplace transform for the integral of the type t to infinity. Now, note that the first one is Riemann integral, given that fu is piecewise continuous, but the second one is improper Riemann integral. And this derivation is not very difficult, and it will follow from the one we have already done for the first case, where the integral range is from 0 to t. The last one requires a little bit of work, and this is again an improper Riemann integral. This is again an improper Riemann integral, and given some conditions, we will derive the formula for integrals of this type, and there are further special functions like the cosine integral and the exponential integral that are covered under this case 3, which are integrals of this type fu over u du from t to infinity. So, let us start with an example of the first one. Another example, we have seen a couple of examples in the last lecture, and let us see another example. So, this is our example for type 1. So, this example is called the error function, and it is denoted by ERFT, and this is by definition the function 2 over root pi integral 0 to t exponential minus u squared du. We know from one of our criteria for existence of improper Riemann integrals that the improper Riemann integral 0 to infinity du exists, and we can evaluate this integral using methods of polar coordinates, and this is a standard integral to evaluate, and the value comes out to be, this value is square root of pi by 2. So, the error function is always between 0 and 1. Similarly, we can define the complementary error function, and this is denoted by ERFC, C for complementary, and this is 1 minus 2 over root pi 0 to t exponential minus u square du. This is nothing but ERFT, and we can rewrite it as integral t to infinity with a factor of 2 over root pi outside exponential minus u square du. So, the first chunk, the error function, is this improper Riemann integral up to t, and the second chunk is from t to infinity. So, we have these two functions, and now we would like to compute the Laplace transform of the error function of square root t. So, one can also compute the Laplace transform of error function itself, but this will be in terms of the complementary error function, and I leave it to you. This is an exercise to show that this is equal to the Laplace transform of the complementary error function is exponential s square over 4, the error function here is equal to exponential s square over 4, the complementary error function evaluated at s by 2. So this is an easy exercise to carry out, and then in this lecture we would like to compute the Laplace transform of the error function of square root t. So let's do that. So the Laplace transform of the error function of square root t is 0 to Laplace transform of the integral 0 to root t exponential minus u square du, and with a factor of 2 over root pi. Now I am going to change this integral which has range from 0 to square root of t, and I will change it from 0 to t by change of variables u square equal to v. So this implies that du equals 1 over 2 square root of v dv, and v ranges from 0 to t now, because u ranges from 0 to square root of t. So v ranges from 0 to t. So then we have the Laplace transform of 0 to t exponential minus v, and then we have 1 over 2 times square root of v dv, and this is nothing but, so 2 in the numerator and denominator cancel out. So 1 over root pi Laplace transform of 0 to t exponential minus v dv over square root of v. So now we can use the formula for this integral, and we have 1 over s times the Laplace transform of e to the power minus t over square root of t, and we know already the Laplace transform of 1 over square root of t, and this is by the first translation theorem, simply replacing s by s plus 1 in the Laplace transform of square root of t. So this is 1 over square root of pi 1 over s times the Laplace transform of 1 over square root of t evaluated at s plus 1, and we know already what is the Laplace transform of square root of t. This is nothing but gamma half by square root of s. So we are going to replace s by s plus 1. So in the end we will get 1 over square root of pi 1 over s and 1 over square root of s plus 1, and in the numerator we have gamma half, but gamma half is actually exactly square root of pi. So this factor and this factor cancel out, and you have 1 over s times square root of s plus 1, which is valid for s greater than 0. So the Laplace transform of the error function of square root of t is 1 over s times square root of s plus 1. Now we come to the second type of type 2 integrals. So these are of the form t to infinity f u du. So we would like to compute the Laplace transform of these kinds of integrals. So we suppose that the improper Riemann integral 0 to infinity f u du exists. So then this implies that the function gt given by t to infinity f u du has a finite limit when t goes to 0 from the right, gt, and so in our notation, g of 0 plus is this integral 0 to infinity fu du. So we can apply our derivative theorem again. So by derivative theorem, we have that the derivative of g is nothing but minus of ft, and so the Laplace transform of g prime t is equal to, first by the derivative theorem, it's equal to s times the Laplace transform of gt minus g of 0 plus, but this is nothing but integral 0 to infinity fu du, and we want to compute this term. So we can take our integral 0 to infinity fu du on the left side, and so we will get the Laplace transform of gt is 1 over s times the Laplace transform of g prime t, which is nothing but the Laplace transform of g prime t is minus the Laplace transform of f, and then we have a plus g 0 plus, and so this is 1 over s integral 0 to infinity fu du minus the Laplace transform of ft, and this is valid for s greater than 0. So we can compute the Laplace transform of gt in this fashion. Now let's come to the type 3 integrals, which are integrals of the form t to infinity fu by u du. So first of all, we should know some conditions under which these kinds of improper integrals exist. So I'll state a theorem, and this is called Dirichlets test. It's a special case of Dirichlets test, and this gives you a sufficient condition for the existence of this kind of integral, fu over u du, and this states that if there exists a constant m greater than 0 such that this integral from t to r fu du is less than or equal to m for all r greater than t, then this integral t to infinity fu over u du exists as an improper Riemann integral. This is a special form of Dirichlets test where you have a product of two functions. One function is fu, the other function is 1 over u. So in general, if phi u is a function which is bounded and monotonically decreasing to 0 as u goes to infinity. This of course 1 by u satisfies this condition. 1 by u is bounded by 1, and we have it that it is monotonically decreasing to 0 as u goes to infinity. Then this integral t to infinity fu over u, fu phi u du exists with the same condition that all the Riemann integrals from t to capital R of f are bounded above by a constant m. So with this sufficient condition, we can determine what kind of functions f gives you an improper Riemann integral of this form. So with this in hand, let's try to compute the Laplace transform of t to infinity fu over u du. So I will make a formal computation, and which will involve some interchange of order of integration, but one has to justify those changes as well. So I will go back to that problem later on, but first let me formal computation gives you this formula where fu over u, the Laplace transform of this integral, is given by 1 over s integral 0 to s f lambda d lambda, where fs is the Laplace transform of ft. So formally we will have this formula. Let us try to compute this. So the Laplace transform of t to infinity fu over u du is given by 0 to infinity and then t to infinity fu over u du, and then you have exponential minus st dt. So in the inner integral, I will make a change of variables u equal to tv, so that v now goes from 1 to infinity and du equals to t dv. So now we can write it as 0 to infinity and then 1 to infinity f of tv over v dv exponential minus st dt, and now we can try to swap these two integrals, and this has to be justified by some sufficient condition which will allow us to justify our change of order of integration. So suppose that this is true, suppose that we can change the order of integration, then we have that the Laplace transform of this integral fu over u du is equal to, so first we had 0 to infinity, then we had 1 to infinity f of tv over v dv exponential minus st dt, which is now equal to 1 to infinity 1 over v integral 0 to infinity f tv d exponential minus st dt, and then you have integral over dv. So notice that since v is greater than 1, this can be written as f of s by v over 1 by v, supposing that fs is defined for all s positive. So then you get 1 to infinity 1 over v 1 over sorry, there should be 1 over v again, 1 over v f of s by v dv. So this is dv over v squared, and now I can make another change of variable lambda equal to s by v, which means that when first of all d lambda is minus s by v square dv, and lambda goes from s to 0. So now we can rewrite this as minus s to 0 f lambda d lambda, which is nothing but S0 to S f lambda d lambda. Now here we have made many assumptions, first of which is that f of S is defined for all S. Second is that we can change the order of integration in this computation, and the third one is that this integral exists. So given these assumptions, this formula will hold.